In this session, we are going to discuss about two important concepts. One is Calomel electrode and another one is glass electrode. To start with Calomel electrode, which comes under a broad heading of reference electrodes. Reference electrodes are the electrodes whose potentials are fixed and known, and these electrodes are used to determine the potential of any other electrode. So Calomel electrode construction is simple, which consists of mercury along with mercury-mercurous chloride paste at the bottom of this glass tube of the Calomel assembly. Rest of the glass tube is filled with saturated KCl solution, and a platinum wire is provided for the contact, that is electrical contact, which is in turn connected externally to a copper wire for connecting it to the device. So this is a brief construction of the Calomel electrode. So we will see, as I already mentioned, Calomel electrode is a reference electrode which can act as both anode as well as cathode based on the other electrode connected to it. That means if the other electrode preferably undergoes oxidation that acts as anode, then Calomel will act as cathode. On the other hand, if the other electrode connected acts as cathode, Calomel will act as anode. That is the meaning. So we will see what are the reactions that takes place when Calomel acts as anode and when Calomel acts as cathode. In the first case, when Calomel acts as anode, oxidation should happen. During this process, mercury will undergo oxidation to mercury plus electron. But once this Hg plus is developed, this Hg plus will react with Cl minus ions and becomes Hg2Cl2 mercurous chloride. When you balance the reaction happening at anode, you will see the reaction is 2Hg plus 2Cl minus giving rise to Hg2Cl2 plus 2 electrons. Similarly, if you see the reaction happening at cathode, that is when Calomel acts as cathode, you will see that reduction should happen. For the reduction process, mercurous chloride will give rise to Hg plus Cl minus. Thus formed Hg plus will receive the electrons and becomes Hg. If you balance the reaction happening at cathode, you will see that Hg2Cl2 receives 2 electrons, becomes Hg plus 2Cl minus. Careful observation, you can find out that the reaction happening at anode is exactly the reaction happening at cathode. So that is, it is reversible. So if you write the Nernst equation for this reduction process, you will get the equation like this: E is equal to E naught minus 0.0591 divided by 2 because number of moles of electrons involved is 2 into log of concentration of Cl minus whole square. 2 moles of Cl minus involved. So rearranging the equation, you can see E is equal to E naught minus 0.0591 divided by 2. Log of Cl minus square can be written as 2 log Cl minus. So the equation will take this form, that is final form of Nernst equation for Calomel electrode. So that is E is equal to E naught minus 0.0591 log of Cl minus. So this is how the Calomel electrode will work as anode, as cathode, and develops a potential according to the Nernst equation given at the end. So few points we have to remember. The points to be remembered with respect to Calomel electrode as follows. So the electrode potential of Calomel is 0.242 volt when we use saturated KCl solution in the Calomel electrode. And it is clear from the Nernst equation and the anodic and cathodic process that Calomel electrode is reversible with respect to chloride ions. So as the concentration of chloride ion changes, potential changes. That means if the chloride ion concentration is high, potential will be low. If the chloride ion concentration is low, potential will be high. So third point is Calomel is used as reference electrode in many of the electrochemical processes. In specific, the Calomel is used in the determination of pH of any solution and potentiometric titration where redox titrations are involved. In that case also Calomel will be useful. So this is very important. The next important concept is the ion selective electrodes. So the ion selective electrodes means they are selectively sensitive to a particular kind of ion that is specific to an ion and develops potential around them based on the concentration of the particular ion. These type of electrodes are referred as ion selective electrodes. For example, you can consider glass electrode. This glass electrode is sensitive to H plus ions. That means in a combination of many ions, glass electrode selectively sensitive to H plus ions and develops a potential based on the concentration of H plus ions only. Now we will see how this glass electrode looks like, what is the construction part of it, how it will work. So the glass electrode will look like this. It is a long glass tube with a glass bulb at the bottom. This glass bulb inside it is filled with 0.1 molar HCl. An internal reference electrode is used, which is silver chloride electrode. The glass membrane is made up of a special type of glass, which is called as Corning glass, and this Corning glass constitutes of 23% by weight of sodium oxide. So an enlarged view of this glass membrane, if you see, it looks like this. A glass membrane in contact with the analyte solution, whose pH we have to determine. When you bring this glass electrode, that is glass membrane, in contact with the analyte solution, you can see that there is a concentration difference created because of 0.1 molar HCl present inside the bulb and H plus ions present outside the bulb in the beaker. So then there is a difference in concentration. This difference in concentration results in a difference in potentials. So how this potential will be converted into pH reading, we will see step by step. Before that, so the representation of this glass electrode, you can see glass electrode, it is represented as solution to be analyzed. That is a solution we are going to take in the beaker, which may be any acid, which is separated by membrane glass. Internal solution is 0.1 molar HCl solution present inside the bulb, and internal reference electrode is AgHCl. This is a brief construction of this glass glass electrode. It is represented like this: silver, that is Ag bar AgCl solid bar 0.1 molar HCl separated by glass membrane. So this is a brief construction part of it. As I already mentioned to you people, internally we have HCl solution of 0.1 molar and externally we have H plus ion solution, that is any acid, of concentration C2. Assume that instead of 0.1 molar HCl, the concentration in general as C1. Then the corresponding potentials developed due to the concentrations C1 and C2 be E1 and E2. So this difference in potential between the junctions E1 and E2 results in a net potential. We call it as boundary potential, which is represented as EB. So this EB, how it arises, we will see. Before that, we can write the Nernst equation for this E1 and E2 as E1 is equal to E1 naught plus 0.0591 by N log of C1. Similarly, if you write the Nernst equation for E2, it will look like E2 is equal to E2 naught plus 0.0591 by N log of C2. So you can see, if you define what is boundary potential, it is nothing but the difference between the potentials E1 and E2, which is written as EB is equal to E2 minus E1. But one point you have to note here, E1 naught and E2 naught are standard hydrogen potentials. That means hydrogen electrode potential under standard conditions. So all of us know that. So standard hydrogen electrode potential is 0. Hence E1 naught becomes equal to E2 naught. That becomes equal to 0. And one more thing is, number of moles of electrons involved in this process is 1. Because we are talking about H plus ions. For H plus ions, N is equal to 1. Considering all these things, we can write the EB, that is boundary potential, as 0.0591 log of C2 minus 0.0591 log of C1. If you carefully observe, C2 is the concentration of the analyte, what I am placing outside this glass membrane, outside this glass membrane, glass electrode. That concentration of that analyte I can change at any point of time. Means this C2 can be acetic acid, formic acid, HCl or any acid of my choice to be determined for its pH. However, this C1 concentration what we are seeing, it is present inside the bulb and it is sealed, which is 0.1 molar HCl, which cannot be changed according to the wish. So its concentration is fixed. So C1 is constant, log of C1 is constant, 0.0591 log of C1, including minus it is constant. So I will rewrite the boundary potential equation as Eb is equal to K plus 0.0591 log of C2. So this is the potential equation, but now consider this case, what will happen when C1 becomes equal to C2? That's what we are going to see. Now see, C1 is equal to C2, then what should happen? E1 and E2 potential should become equal. If E1 and E2 becomes equal, then boundary potential should become 0. When boundary potential becomes 0, glass electrode potential also should become 0. However, glass electrode potential will not become equal to 0. Still, glass electrode will be able to develop potential because of two more different types of potentials which are coming into picture. So what are these two extra potentials which are coming into picture are named as E asymmetric potential and EAG-AGCL potential. So what is E asymmetric potential? This is an asymmetric potential arising due to the uneven nature of the glass membrane or asymmetric nature of the glass membrane. So that means the roughness of the glass membrane determines this asymmetric potential. And EAG-AGCL is an internal reference electrode used in the glass electrode, whose potential also to be taken into account in order to estimate the potential at glass electrode. So that's why considering all three, glass electrode potential can be written as the sum of boundary potential plus asymmetric potential plus silver-silver chloride potential. So now we know that what is boundary potential. In the previous step we have derived. Substituting that boundary potential EB into this equation 2, we will get EG is equal to, EB is nothing but K plus 0.0591 log of C2 plus as usual E asymmetric plus EAG-AGCL. Careful observation will tell me that K is a constant. Asymmetric nature for a given glass membrane is same, so E asymmetric becomes constant. Silver-silver chloride is a reference electrode whose potential is constant. So all three constants together, I will write it as a single constant which is named as E0G. So the equation will take this form, Eg is equal to E0G plus 0.0591 log of C2. And all of us came to know that C2 is the concentration of the analyte we are placing in the beaker and bringing that glass electrode in contact. So instead of telling this acid concentration, that is acetic acid or HCl concentration, any acid, irrespective of that, it is a concentration of H plus ions. Whether it is acetic acid or formic acid or any acid, it is concentration of H plus ions. Instead of C2, I can write it as H plus ion concentration. So equation will be in this form. Now, all of you know that pH can be represented as a negative logarithm of H plus. So instead of log of H plus, if I substitute this into the previous equation, the equation will take this form, Eg is equal to E0G minus 0.0591 pH. So this is very, very important equation. So how this glass electrode potential is developed and how it is turned into pH, it will be known from this. However, in a practical situation, how we are going to determine the pH of a given solution, we are going to see. So that is determination of pH using glass electrode. For this, a simple construction is required like this. You are going to consider glass electrode in combination with Calomel electrode. All of us know that single electrode potential is not easy to find out. So what we are going to do, we are taking glass electrode in combination with a reference electrode which is external, that is Calomel electrode. Both the electrodes are connected to a pH meter or voltmeter. So these two electrodes we will bring in contact with a solution of unknown pH. So based on the concentration of this solution, a potential will be developed because of this combination. That potential we call it as cell potential. And all of us know that cell potential can be given as E cathode minus E anode. Here in this case, glass is acting as cathode by default and the calomel is acting as anode. We can write the equation E cell is equal to E glass minus E standard calomel electrode. In the previous derivation, we have derived that glass electrode potential can be written as E cell is equal to E naught G minus 0.0591 pH minus E standard calomel electrode as it is. Now I want an equation for pH. I will rearrange this equation. Minus 0.0591 pH, I will take it to the left side. Rest of the terms, I will send it to right hand side. The equation will look like this. So finally rearranging it to pH, you can see that pH is equal to E naught G minus E cell minus E standard calomel electrode divided by 0.0591. So this is a very, very important equation from which the potentials developed due to the combination of glass and calomel electrode will get converted into pH readings that will be digitally displayed by a device called pH meter. That's how directly you can find out pH of any solution of your choice by immersing glass calomel electrode assembly using this